let's continue with actin. We have seen many actin binding proteins. They can do several shapes, but we are going to start now with the motor proteins. Just like kinesin and dynein, there are motor proteins walking on actin, and they're called myosin. There are two kinds of myosins, myosin 1 and myosin 2. Myosin 1 is used to make the contractile bundles. You see here, they are like tiny muscles, but they are not real muscles. And this protein, it doesn't have 2 feet like kinesin. It has one head domain and a tail domain. Okay, this head and tail, they have different purposes. This head, and for me it should be feet, they are touching the actin cytoskeleton, interacting with the actin, and they walk on it. Okay, of course, because they are interacting with actin, they know which direction is going, because you see the surface of actin is asymmetric. So one direction of actin is different from the other direction. So they can carry stuff to the plus direction or minus direction. Okay, here we cannot say that the plus direction is always inside the cell, the minus direction is always cytosol, no, centrosome, no. But all in all, they can know the direction and go, and they can carry vesicles just like the kinesins do. This head domain is kind of straightforward. All myosins won't have the same head domain, but the tail domain can be different from protein to protein. The tail domain, for example, can attach itself to the plasma membrane, and it can push the plasma membrane against the actin beneath. So it is going to mobilize the plasma membrane against the internal contents. It's also useful for the crawling behavior. You know, the cells, they change shape, they mobilize themselves on a surface. You have seen previously inner side of the cell animation. That was great. And there it shows how it can change shape and crawl between cells. Okay. And the second type of motor proteins that we are going to talk is real muscle proteins, myosin 2. But first, there are 3 kinds of muscles in our body: skeletal muscle, cardiac muscles, and smooth muscle. Cardiac muscles, they are structurally like skeletal muscles, but we cannot control them. Okay, they are not in our intellectual control. When you want to move your arm, of course you can move your arm, but when you want to increase your heart pace, you cannot increase it. And there are smooth muscles, you cannot control them anyway. You cannot give orders to your stomach with your frontal cortex. Okay, this is not cognitive behavior. Of course, your brain is controlling both the cardiac muscles and smooth muscles, but this is not cognitive behavior. It's another type of control, which is under control of some older parts of your brain, which is responsible of keeping you alive. Okay, this is myosin 2 molecule, and unlike the myosin 1, which was monomer, this is a dimer. Now there are 2 heads, and the tails are wrapped around each other, so it creates the structure. And to make a myosin 2 filament, you have to gather all of them. Now, there's a dimer here, a dimer here. Check the direction. The heads are looking this way, the tails are looking this way. Now, on the other side of the myosin 2 filament, there is the dimers are organized in the other direction. Okay, heads are here, tails are here. Okay. So both heads here and heads here. And when there's a myosin 2 dimer, they are side by side. Again, they are interacting with the non-covalent interactions. And in the middle, it is only tails. So we call it bare region because the heads are much thicker, bigger, the tails are much thinner. So if under the microscope, they look smaller. So what you can do with myosin 2 is that when you have 2 actin microtubules and when you have a couple of myosins in between them in the reverse orientation, because these heads can walk on the actin, it can mobilize these actins, or all this mobility is just relative. So at the end, it can pull them together. The actin cytoskeleton can start this way with a couple of myosins between them, and when you apply energy, they are going to move, and what you're going to end up is this. Now, shifting from this position to this position has a very well-known name. It is called contraction. All the muscle contraction we know, they work with this principles. The myosins here, they move on the actin surface, so they are either dragging actin or because they keep stable, and at the end the actins move. And in the muscles, which are made of actually myofibrils, the working principles are exactly the same. You have seen these discs, sarcomeres, for a long time. Let's check closely what is a sarcomere. In the sarcomeres, first you have the Z disc. The Z disc is in a fixed place. Okay, the Z disc doesn't move, which it is what it keeps the physical support from. Here in this light place, you have the actins. So these are the roads that the myofibril 2 motors are walking on. So this is the root, and this is myofibril 2, which is the motor. So when you supply energy, when it finds ATP, what is going to happen is that these myofibrils, they will walk on the actin. So these guys, they will walk on this direction, and these guys, they will walk on this direction. So they are pulling in two opposite directions. Of course, it is not possible because the tails are strongly holding each other. So they are going to stay stable. What is going to happen instead is that the actin monomers are going to mobilize. Okay? So when you provide ATP, these motor proteins, they will use the ATP to pull the actins close to each other. So you will end up with this, which is called contraction. And then these heads will release the actin, so it will relax. It will come back to the original conformation. Okay, and let's check the molecular form, how it is happening. It happens in 5 stages. This myosin head is connected to actin surface, normally attached, and when it has the ATP, it released, and then it moves. It makes a movement from here to here by hydrolyzing the phosphate, which is spending ATP. So instead of this, it binds to the next actin, this, and then it moves. Of course, when it moves, relatively, actin is moving to the opposite direction. Okay, so step by step, from here to here, here to here, here to here, it walks on the actin cytoskeleton, and this is what we call muscle contraction. Ever heard of rigor mortis? When the animal dies, this movement is not available anymore. The heads, they stay attached on the actin cytoskeleton. So even if you force the muscles will not move. So the dead animals will be very hard for a while. Rigor mortis means the dead hardness, the stiffness of the dead animal, and I'm not sure Rick and Morty got the name from rigor mortis. So how does the muscle work? Once again, we know that, the muscles are innervated by nerves. These nerves, they bring the signal to the muscle surface from long distance, and once they receive on the muscle surface, they initiate the muscle movement. To initiate the muscle movement, they use calcium. And now we know that calcium is a very mighty messenger because it's small, because it can diffuse very fast, and because the intracellular calcium concentration is nearly zero. And we know that the cytosolic concentration is zero because all the calcium is stored in the ER. This time we don't call it smooth ER. This time we call it sarcoplasmic reticulum. Okay, here it has the calcium. Once the nerve releases the signal to the muscle, calcium is released from here to the muscle, myofibrils, and then the muscles will contract. Okay, and how does it happen? I said that ATP is required for the myofibril, for the myosin 2 to work on actin, but the reality is that ATP is always here. I mean, in the muscles, we always have ATP. There is no situation that ATP is not available. So what prevents the muscle contraction is not the lack of ATP, but because the surface of the actin cytoskeleton is not available. Remember, there were actin binding proteins. Some of them surrounds the surface and makes it unavailable. It hides the actin cytoskeleton. Okay, here the tropomyosin complex and troponin complex, they hide the actin cytoskeleton by covering the surface. So even if the myosin 2 is here, the myosin 2 cannot interact with it, even if it has energy. So first, you have to set the actin free, and it happens with the help of calcium. When calcium comes, the tropomyosin blocking muscle myosin binding site shifts, and when it shifts, these proteins will shift all together. It's going to make the surface available. So although, anyway, ATP is here, this myosin 2 is going to use ATP to walk on it. So as long as the surface of actin is available, the muscle will be able to use it to walk on it. But for the relaxation, again, this shifts back, comes to the original position, and the muscle is not available anymore, so the muscle contraction will stop, which is